Okay. Okay. So, and everybody, okay, I need to make sure that the thing has started first. No. Okay, the recording has started. Cool. So, can everybody see my PowerPoint screen?
Yes,
Yes,
sir.
Good.
sir.
Yes, sir.
Oh, okay, great. Thank you. Okay. So, in the last class, we, what is this sound? Is somebody's mic on? Can you guys hear a very peculiar sound?
Yes, like that of an insect.
Yes,
Okay.
sir.
It's gone.
Okay, got it. Chalo. Yeah. So, in the last class, we saw that most simple models of population dynamics predict that as the growth rates increase, all kinds of dynamic behaviors are expected. Then a large number of empirical studies tried to document chaos and other slightly more complicated dynamics in the real biological populations. And there was a very peculiar observation. The peculiar observation was that although things looked somewhat irregular, but when people estimated the parameters, they ended up finding that none of them are showing chaos. Okay, and this is in spite of the fact that these populations are having fairly high growth rates. So this is the one study that we examined closely, the Hassel et al. Study, and we ended up seeing that these people ended up seeing that most populations, according to them, were exhibiting very simple behavior, which even intuitively was not making any sense. And so, as I said, second round of work started, where people tried to explain why is it that the simple models that we are looking at, they are unable to show the kind of complicated dynamics when you compare them with real data. So, taken differently, that why is it that real populations are not showing chaos? So there are quite a few very interesting things that happened. I'll just present one or two in front of you guys. So did anybody try iterating a model, either the Ricker model or the logistic model, anything on your own? Did anyone try it? People remember, I can't see the chat box when the PowerPoint is on. So if you have to say something, you have to say it out.
Okay, so I tried doing Ricker and the discrete logistic model.
Okay.
I did time
And
series and the bifurcation diagram.
okay, so if there was a time series, did you see something peculiar in the time series? Did you notice anything off?
You mean like it would continue and then it would reach a low point and...
No, all those behaviors are there, the behaviors we have discussed, but otherwise, have you seen something which you would have looked at and said, this doesn't make sense? Not really?
No.
Okay, fine. Okay. So what I'm going to show you is a small time series, 10 time steps, based on whatever r equal to 3.1, k equal to 500, etc. The exact values don't matter, but so this is what the time series looks like. It starts with 100, and it then in the successive time steps it gives these values. Do you guys see anything off here? Without knowing anything about the model, without knowing anything about the R value, is anything interesting?
It's wildly, oscillating. Maybe.
That is going to happen because I have chosen R equal to 3.1. Fair enough. If I had chosen a lower R, it would not oscillate that violently. Anything else?
Okay, actually these are in decimal points, right? If we convert this into integers, that behavior does not remain the same way. I tried doing that.
Exactly. So if you look at these population sizes, all of them have an integer part and then they have a decimal part. But if you look at real population sizes are always going to be in integers. There is nothing else that can happen. Whereas if you look at outputs from all these models, these outputs are almost always in this form. They have some kind of a decimal part. So what happens if we end up forcing the population to take integer values. And when you do that, as Ruchira pointed out, I assume it was Ruchira's voice, right?
Yes,
Okay.
it is.
Ruchira. So if you do that, then something very peculiar happens. So what you see over here is the normal bifurcation map, and what you see over here is the integerized version. So in this version, what has been done is every time step, the value has been rounded off to the nearest integer, and then it has been fed again into the model. So can you see what is happening? Two things. Number one, in this particular case, you can never see an extinction in the context of the Ricker model. Okay, and the reason you cannot see an extinction is because even if e to the power something, that power part in the exponent, even if it goes to 0, even then e to the power 0 will be equal to 1. You will never end up getting an extinction directly from the model. However, the moment you integerize the whole thing, then you can see that for high values of r, extinctions are coming in. Okay, that's an observation, but that's not a critical observation. The critical observation is, remember we said that when you see chaos, the points never repeat themselves. Therefore, on a bifurcation map, it looks like a complete smear for any given value of r, right? Here, if you look at it, those smears have disappeared, right? Which essentially means here, the moment you have integerized the whole system, now you are also losing out on chaos. Okay. Now, why is that happening? Can anybody tell me why chaos goes away when you integerize the whole stuff?
So is it because you start getting the same number back since you're rounding down to the lowest integer?
Correct. But then why can't I have infinite number of points?
Does it have anything to do with the fact that integers are a countable set and real numbers are uncountable?
But both of them are infinite, right? Countable infinite and uncountable infinite, in terms of what you have, are both infinities. In realistic terms, both are infinities, right? Mathematically, they are different, I agree. But in realistic terms, both are infinities. So why can't I have a huge number over here? Yeah, you guys are actually pretty close. So see, what happens is that we said that one of the properties of a chaotic time series is that it will never repeat itself, correct? Now, these models that we have been dealing with, they are all quadratic in n, correct? You have an outside and an inside, the two will multiply and it will give you a quadratic. So if you have a quadratic, then you are going to have either a maxima or a minima. And you guys can satisfy yourselves very trivially to show that in these cases, these are all maximas. Okay, which means that for any given r and k combination, there is a maximum value that can be reached. You can also see the same thing from this bifurcation map. There is a nice maxima over here. Okay, and howsoever number of times you iterate the whole thing, it will not go above this maxima. Now, you all automatically have a minima here at 0. So between whatever points you need to have, they need to be between 0 and this maxima. Now, we know that between any 2 points, there are infinite number of points as long as you are considering decimals, right? Between any 2 numbers, there are infinite number of numbers, correct? However, the moment you integerize this whole thing, then the number of integers between this maxima and this minima becomes finite, correct? And therefore, you can have, let's say this value is something, some z or whatever. You can have a periodic cycle of a maximum periodicity of z. Once you have exhausted all the possible values in this bound, then the whole thing is bound to repeat. And in practice, actually, it doesn't even go to z much faster than that, much earlier than that, it starts repeating itself. Therefore, very simply speaking, the moment you end up putting in this condition that your state variable, your NT values will only be integers, the deterministic chaos as we know it completely disappears. Okay. Now please note, this is only in the context of the deterministic chaos. Obviously, we are not talking stochastic stuffs over here, but deterministic chaos is going to disappear. Now, if that be the case, then what is it that people are trying to find, right? So, is the logic clear why chaos disappears the moment you integerize the whole thing? Anybody who has a problem with the logic?
Sir,
you
wasn't
said
this
something
known?
Huh? Sorry?
Akash, you go on.
Yeah, I was just saying, wasn't this known when people were first playing around with difference equations, that the populations have to be integers, so you shouldn't use decimal values?
Do you
Like,
see
wasn't
this? Do you see the date over here?
Yeah.
This is the first time that this gets reported formally. Do you see where it is getting reported?
Yes. That's why I'm little surprised that if
See,
people have
that
been
is,
playing since the 60s and 70s, nobody thought of restricting
nobody
the.
did. Nobody did. Nobody did. Can you imagine that? It's amazing. It's beautiful. It's superb, right?
Yeah, it's
It
really
takes-
stunning.
Yes, yes. I mean, you guys got it in what, about 30 seconds or less, right?
Yeah.
Yes. That's one of the beauties in biology. There are lots of low-hanging fruits still around. Okay. Anyway, so there is
Sir,
one.
sir, excuse me, I have a question. Okay.
Just let me make one point, then I'll take the question. Note one thing, that although this is saying that integration is going to kill chaos, you can still have limit cycles of fairly high periodicities. Okay, so it is not saying that everything will become very, very simple, everything will just become a 2-point cycle or a stable point or something. All it is saying is that chaos will not be there. Okay, so this does not exclude complicated dynamics, it excludes chaos. Ab bolo. What's the question?
So you said something about all the points being maxima of something. I didn't get that point.
No, I didn't say all the points are maxima of something. I said that if you look at the structure of the model, the discrete logistic model or the Ricker model and so on, all these are quadratic in n, right? Because you have a Rn and then you have a 1 minus nt by k, so it becomes a quadratic in. So if something is a quadratic in n, then it is going to have a maxima.
Okay.
For a given R and K, the presence of the maxima is guaranteed. The same thing you can see from the bifurcation map, that there is a nice maxima for any value of R. That's all.
Yes. Okay.
Okay. So yeah, so this is the logic, and this is the point that I was making, that deterministic chaos cannot be observed in biological systems, but it does not exclude the possibility of limit cycles with long periodicities. And this particular thing, the integerization leading to chaos, this effect was the original authors called it the lattice effect. Okay, so they thought of population sizes as not being continuous but as discrete points in a lattice, and hence this phenomena of chaos disappearing, they gave it a nice name called lattice effect. Anyway, so this is one. We'll look at one more thing. Okay, this logic is slightly more complicated, but if you think about it quietly, it's not too complicated either. So remember that when we were deriving the equations, the logistic model, the exponential logistic model, we ended up saying that our R values are a constant, which essentially means birth rate, death rate, immigration, emigration, all the rates are constants. Okay, so suppose we still have all those things, but from outside every generation we end up adding some number. Okay, so every generation some constant number C are coming from outside into the population. Now this is something that actually happens quite a bit in real life. So for example, if you guys have heard about source sink populations, so where you have, let's say, a huge say a continent or a big place with lots of individuals, and then some small habitats a little bit away, And these small habitats by themselves, they are non-sustainable, but these guys regularly get migrants from the big place, and therefore their population continues. All right. So this is something which is analogous to this situation. So what we are going to look at is a very simple model. Nt plus 1 is f of nt, where f is the recur function, and to it each generation we are going to add some constant c. Okay, again the k values and the n0 values don't matter. I'm just showing them over here just for the sake of so that you guys, if you want, you can repeat the simulations exactly. So this is what happens when c is equal to 0. So this is the bifurcation map that you have been seeing till now. So now we are adding 10 individuals each generations. Remember, our k is 500, so this is 1/50th of k. Okay, what do you see happening in this zone? Nothing much is changing. However, in this zone, for where you have high values of r, can you guys see my cursor, people, or are you unable to see the cursor?
We can see it, sir. We can
We
see
can
it.
Oh, good. Then that makes my life easy. So in this zone over here, can you see that the dynamics is becoming simpler, and what was earlier chaos, now you are getting limit cycles of not very high periodicities. Cool. We increase c a bit more, and now you see that for a larger zone of R, essentially chaos gives way to simple dynamics. Okay, just a 4-point cycle. We increase c further to 30, and again remember, this is not too high in the context of what my k is. And what do you see? You see that chaos completely disappears, and you only have simple dynamics. You increase r further, so here for c equal to 30, you still have, let's say, a 8-point cycle in some zone. So you have 2 point, you have 4 point, you have 8 point, then again you have 4 point, and then you have 2 point. When your c is 40, then you only have 2 point and 4 point cycles, and when your c is 60, you only have 2 point cycles, right? So essentially what has happened is that if each generation you end up adding a few individuals, you end up completely getting rid of chaos. Okay. Now, Bola?
Hadn't we included C already in R?
So that's the point. If you can do that, okay, but if here we are doing the model slightly separately, we are essentially saying that the dynamics by itself is whatever it is, and on top of that, extra 10 individuals are being added, 20 individuals are being added. That's all.
Okay.
Mathematically, you can push it over there. Okay, but if you don't push it over there mathematically, if you just do it this way, then this is the observation. All right,
sir.
हाँ बोलो.
When you're adding these individuals, why is the chaos disappearing? इसका कोई intuition है क्या? Oh wow.
इसका इंट्यूशन बहुत वेल नोन इंट्यूशन है. थोड़ा सा सोचोगे तो निकल आएगा. And I'll leave it to you guys, and then whenever we meet next, I'm going to discuss this. Okay.
Okay.
But have fun trying to figure this out. By the way, the guy who figured this out published this in Nature. Okay, it's a Nature paper.
Right.
Yeah, but it's very simple. It's not as trivial as the integerization one is, but it's pretty simple actually. You guys just have to look at it, look at this thing, and think about how chaos operates in your head for 10 minutes, and automatically you will get it. Okay, but it will take you 10 minutes.
Okay.
So what happens if we have integerization as well as this?
Good question. करके देख लो. What if happens if you have integerization as well as this? Something else will happen. Check it out. See, just one second. See, anyway, the moment you do integerization, chaos will disappear on its own. Okay, so you will get something. It will be, the observations will not be this clean, but you will get analogous observations. What exactly it will be, you guys can check it out. Bolo.
Yeah, so in the log model, when you consider the R, okay, the rate of increase, that doesn't really consider the immigration, right? I mean, otherwise
By itself, the immigration is not there.
it's not there in the R either, right? Means you have to add it somewhere else.
See, the point is that the R is essentially the rate of increase. Okay, rate of in some sense, the intrinsic rate.
Yeah,
So you
intrinsic
can,
rate.
yeah, so you can consider that the intrinsic rate has all those B, D, I, E all put in one together. Okay.
Yeah. So, but the thing is, sir, the realized growth rate would go on decreasing as you increase the population,
Exactly.
but the
Exactly.
immigration won't.
Exactly. So the C is not exactly analogous of putting it over there. Precisely. Okay, if you put the C over there, then the realized growth rate through the entire thing will come down. But here the C is just always there on the right hand side. This plus over here.
Yeah. So
And
like
that
there is a continuous immigration in a sense.
exactly, and that is your clue about how to figuring out what's happening here. Okay.
So, but like, how realistic is this continuous immigration?
See, this is something that can be, for example, when you guys have captive breeding programs. You know what is captive breeding? So many a times populations are not sustainable, natural populations are not sustainable in nature. Therefore, what you do is you get hold of zoo populations or some other breeding programs, and then from there you regularly put these individuals into nature. Okay, so that's exactly equivalent to doing this plus C.
So, but according to the model, even the plus C, the new ones which are coming, they are not increasing the competition, right? Or are they?
They are not doing what?
They are not reducing the rate of growth, right? The additional ones.
See, these guys are not reducing the growth in that generation, but they are contributing to the population growth in the next generation. Because they are breeding, they are getting, the population size is increasing by plus C, no?
Okay.
Correct. Okay. So figure this out, and if you guys can't figure out, then I'll tell you, what the thing is and where to look at it. Look for it.
So this is mathematical, like similar to addition, even subtraction should work, right?
That's PNAS paper actually, where they ended up looking at addition and subtraction. And that paper actually is one of the most famous papers. Have you guys heard of this lady called Somnatta Sinha? Started her career in CCMB, was in ICER Mohali for quite some time.
Tiger person.
Sorry?
Tiger, like the person.
No. She's not a tiger person. She's a very, nice simulation person. Only works on computers, doesn't go to the jungle. So yeah. So that was Somnatta Sinha's work. What will happen if I subtract? And actually, in this particular case, what I'm showing you is for the Ricker model. If you do this for the logistic model, you might end up getting slightly different answers. Okay, and all of it is connected. All of the underlying theory, because of which you getting all these changes remain the same. The way the changes manifest themselves depends on which model you end up taking. Okay, how all that works, figure out. Okay, let me put it simply. Don't get into the complications right now, just figure it out for the Ricker. Once you have figured out what the underlying mechanism is, then you can apply that mechanism to any model and ask yourself what the changes will be like. Okay, if you get into the complexities straight away, then it will be a big issue. But remember this name, Somnatta Sinha, PNAS 1995, I think, is 93 or 95, one of the 2 years when this rather famous PNAS paper comes out. Okay. Anyway, anything else?
No, sir, that's it. Thank you.
Okay, shall we proceed? So, let me see how much time is remaining.
So sorry, just one more thing. We see that chaos again immediately, like very sharply disappears at some value of R. So like what determines that value of R? See, if you see the C is equal to 20 graph, you see that at some value between 3 and 4, the chaos very suddenly disappears. Again,
Yes.
why is there not a sort of a gradation between the like
No. There is a gradation. There is a gradation, and the gradation depends on the values of C. Okay. So if you look at it, I'm changing C's in step sizes of 10. If instead of changing C in step sizes of 10, you change C in step sizes of 1, you will see a more gradual thing.
Sir, I'm not talking about changing C. If you see one particular graph where you fix C, say C is equal to 20, in that graph, when you change R, so at one value of R, there's a sudden disappearance of chaos.
You are talking around this area, no?
Yes, sir. So why is there not a smooth transition from chaos?
No, see, when it comes to chaos, these transitions are always abrupt. So even if you look at the unintegerized model, see the transition from single point to 2 point is abrupt, 2 point to 4 point is abrupt. Okay, all these transitions in the chaotic trajectory are always abrupt. And the reason for that is very well known. You have to do the stability analysis, and you will find that these have to be abrupt changes. These changes cannot be gradual changes the way you are thinking. So I'm going to give you guys the May 1976 paper. If you are into maths, then look up the stability analysis and you will figure out why that is happening. Okay, there's nothing magic in it. It's simple.
Okay, thank you.
Okay, chalo. So now we look at something slightly more interesting. Okay, now remember that the Hassel et al. Work that we looked at, those guys were looking at a model which was of the type, let me see if this works, yeah, which was of the type nt plus 1 is equal to f of nt, correct? Where this function f was a reasonably simple function. All right. Now, these two people, Peter Turchin and Andy Taylor, in a very famous paper in 1992, asked whether this peculiar observation that the models seem to be very simple, can this be a function of this particular choice that these guys made? This taking this kind of a very simple model, can that be the reason for which Hassel et al. Ended up getting the results that they got? So remember, when we were talking about how to detect chaos, I said one of the issues with that second method of parameter estimation is that you need to say that I know that my model is the best. Okay, you need to have some very strong a priori reason for suggesting that this is the best model to use. And unfortunately, most of the times we don't really have that. Okay, so there is a bit of faith going on over here. So what Turchin and Taylor did was they said that forget about choosing a model a priori. Let the data tell us which is the best model to look for. Okay, so what they did was they took the time series, and also what they did was actually fantastic. They took, I think, 14 of the original time series that Hassel et al. Had taken, and then they also took a bunch of other time series from vertebrates, mammals, birds, etc., etc. So they had much larger number of time series, and for each one of those time series, what they did was, instead of fitting a mechanistic model like Ricker or logistic, they essentially ended up fitting polynomials. Okay, now you guys know that if you increase the complexity of a polynomial, then by having a sufficiently complex polynomial of a sufficiently high degree, you can basically fit any trajectory, right? All the points can be fit. So obviously, when you take polynomials of higher and higher degrees, with higher and higher power, with higher and higher complexities, then your fit is going to improve at every step. That's trivial. So what they also did was they put in a penalty function. So they said that for each model, for each increase in the complexity of my model, I am going to penalize the betterment of fit by some measure of how much, the fact that I am increasing my parameters. So doing this, so there are some very nice information theoretic measures that can be used. The precise one that they ended up using over here is known as Akaike Information Criteria, AIC, which is pretty commonly used. And doing all that, so they did one more thing. So if you look at this, Hassel et al.'s formulation, it is NT plus 1 is a function of NT alone. They said, what if that is not correct? What if this is a function of not only NT but also NT minus 1, also NT minus 2, and so on? So what they ended up doing was, so that's how the polynomial is getting constructed. So they took higher and higher lags, and then instead of taking a simple functional form, they ended up choosing different kinds of functional forms. And they also did all kinds of transforms, so what is known as Box-Cox transforms. And doing that, they essentially, for each time series, they ended up coming up with a suite of models, not one model but a suite of models. And then they fit each model to the data set and did this penalization business that I talked about. And then from that, they tried to figure out what is the optimal model. What is the model that best describes that data set? And then once they figured that out, then from that, they extracted the parameter values and then asked the question that for these parameter values, do I expect a monotonic damping, or do I expect an oscillation, or do I expect chaos? Okay? Is the method becoming clear?
Sir, I didn't understand the penalization thing that you
see.
explained.
You got the point that these guys are using NT plus 1 is f of NT, NT minus 1, NT minus 2, and so on, correct?
Yes. Yes.
Now, how are they getting this f? For the f, what they are doing is they are simply using polynomials. Okay? Now, when they are using polynomials, and they are using polynomials of different degrees and orders. Okay, so the power to which they are raising are different, and they are also transforming this NT. Okay, different kinds of transforms, log transform, square root transform, square transform, and all that. Okay. So when you do all these things, so the transforms are okay, transforms are not an issue, but when you increase the complexity of a polynomial, we know that by having sufficiently complicated polynomial, you can fit any data, right? Every single point can be fit.
Avoid overfitting, they're adding. Okay, fine, got it.
Exactly. So they are avoiding overfitting by figuring out what is the optimal complexity of the model which needs to be fit to that data. Okay?
So how do they decide the value of penalization?
So that's where they came up. I said they use something called the Akaike Information Criteria. Okay. Yeah. So you guys just look up this thing, AIC. Okay. Akaike Information Criteria. Okay. These are very standard things. Because we are talking ecology over here, that's why I'm not going into these things, but I'm going to give you guys papers from where you can look up all these definitions and so on. Okay? So this is what I was saying. They fit a large set of models with different number of time lags and varying complexity, and from that they figured out the optimal model, and from there onwards it was the same as what Hassel et al. Did. So from those parameter values, they asked that based on these parameter values, what is the dynamics that I am expecting? And when they did that, they actually found that you are getting all kinds of behaviors. You are getting damping, exponential damping, oscillatory damping, limit cycles, chaos. Everything is there in the natural time cycle, in the natural time series. Okay. So they came up with a fantastic conclusion. They said that when you are reconstructing the endogenous dynamics, so reconstructing endogenous dynamics means that you are trying to figure out what the endogenous dynamics is based on the parameter values. So they said, if you are using simple models of this, NT plus 1 equal to FNT type of models, for doing this, then you are in general going to be biased in terms of finding stability. Okay. Put differently, the level of complexity of the model that you end up using is going to, or it's possible to get biased by that in terms of coming to conclusions, coming to inferences about the nature of the time series in front of you. So this, if you think about it closely, is a very, very non-intuitive thing. Okay, this is suggesting that even if you have some theoretical justification for choosing a particular model, if there is more complexity in the underlying dynamics, then that simplified model is completely going to screw you in terms of understanding the dynamics. So be very, very careful about choosing a model of optimal complexity. Now, for this, I'll give you guys a visual analogy. So, see, whenever you have a system is essentially something which is in a multidimensional space, which basically means that it is getting affected by multiple things. Now, when you are trying to model it, what you are doing is you are essentially taking a projection of that system on a simpler space, a two-dimensional space or a three-dimensional space, your model space, and based on whatever you are seeing being reconstructed in that two-dimensional, three-dimensional space, you are trying to figure out what the system is doing in the higher dimensional space. Okay, that is modeling by definition. Now, many a times, even if a system is highly complex, so for example, this rather complicated shape over here, the projection that you get in the lower dimension can be very, very simple. And therefore, you should always, everybody can see this shadow, right, which looks exactly like a cube. But obviously, this thing is not a cube. So, you have to be very careful in terms of saying anything about the original multidimensional beast based on the simplified stuff that you see in the lower dimension. Typically, you end up thinking that if this is complicated, even its projection will be complicated. But that is not always true. Sometimes the projection can be simple. Okay, so that is the main crux over here. Not everything that is complex has a simple, complex projection. Some complex guys can even have simple projections. So this is in general true of life. Many a times, you have a situation which is very, very complex, but if you look at it from a certain angle, it looks as if it's just very simple along certain axes, and many a times you end up taking your decision based on those simple things, which in short term might work out. In the long run, more often than not, they end up screwing you. And second thing is, as I said, this is just an analogy. Okay, don't take this as a 1:1 mapping. It is not. Okay, so this ends this particular topic over here. The references, etc., I'm going to give you guys. Now, one thing that we still haven't done is figuring out the kind of mechanistic model that I talked about right at the beginning. So we had models which are mechanistic, which are taking some biological features into account, and then we showed that where those things kind of fail in after a point. But we still haven't taken a model which is taking biological realities almost from first principles and then building something where you can have a direct 1:1 mapping between the biological things and the observed dynamics straight away. Turns out that these kind of simple models are in general capable of giving you that kind of inference, but there are other slightly higher order models which can do that. Normally I don't cover it in the class, but since some of you have been expressing interest about this, I will end up doing one class on that, which is the next one. Okay. So where are we? We have about 3-4 more minutes. So any pressing questions?
Sir, in the analogy, so what is actually the projection which we are comparing here? So are the models, the idealized models, being compared with the projection?
Yes. The
Okay.
shadow that you saw is the projection, and the shadow is analogous to the model. Correct.
So what is the relevance of this study showing us that simple models can lead us to expect simple behavior, when anyways we've seen that if you integerize the models and make them realistic, the chaos disappears? Do you get what I'm trying to say? Like, if integerized models automatically eliminate chaos, then what is the point of saying that simple models may be biasing us to avoid expecting it?
No. See, the Hassel et al. Study has two problems. One thing is it is showing that chaos is not there. That is fine. But the bigger thing is that it is showing that everything is monotonic damping. Remember, 20 out of 24 is monotonic damping. So the second part is against that. Okay.
Okay.
Yeah. Okay. So there are lots of stuffs over here. I don't know. What is SMH? I have no idea. Looks like a Feynman diagram. What looks like a Feynman diagram here? Parijat? Yes, C is individuals added each generation right from beginning. Yes. Okay, so the difference between C and R we discussed in response to somebody's question. Is it clear now, Subrajit? The difference between C and R, is it clear? अरे यार हाँ ना कुछ तो बोल दे. Hello.
Yes, sir, you are audible.
Okay. Can C be negative also? So this was also discussed. Yes, you can have negative C. So if you have negative C, then that is immigration. Okay. So yeah, see, then that will become immigration, and as I said, that has its own great things. On Earth, there is no immigration or immigration as a whole. Integration is also a little chaotic, but net effect there is no chaos. क्या है यार? Philosophy हो रहा है क्या? Okay, chaos plus chaos equal to simplicity. Area 51, exosperm theory. My goodness. Okay. Yes, this is not about communities ecosystems. That's correct. Lyapunov exponents don't really give you a measure of chaosness. Okay, so essentially, when the Lyapunov becomes positive, it is okay. I see what you guys mean. Since it is the rate at which the divergence is happening, therefore, yeah, okay, maybe you can say that. Fine.
So I was asking in my original question that is there a scale which we can justify, like what is less chaotic and what is more chaotic?
Typically, people don't do that. Typically, chaos is taken as chaos. Okay, you can talk in terms of amplitude of fluctuation, but otherwise, I don't think this distinction is typically made in the literature. But yeah, sure, you can always say something like this has a greater Lyapunov and that has a lower Lyapunov. Okay. There, so what is meant by complexity in polynomials? The complexity in polynomials is going to be in terms of primarily how many terms are getting added. So are you doing it just nt minus 1, or are you doing nt minus 1, nt minus 2? It also is about to the powers to which you are raising them, and so on. See, the point is that R is the intrinsic rate of increase. Now, when you have R, then that intrinsic rate is getting scaled by that function which is inside the bracket, correct? So, even if that R overall is constant, the realized R is not a constant, that is coming down, based on what your population density is. That's density dependence by definition. Now, this immigration C, this immigration is happening irrespective of what the realized growth rate is. So in that sense, it is independent of it. Okay.
Sir, adding to this question, so basically the C is independent of R, but R depends on C, right? Because of C, R will reduce further, right?
No. See, what is happening is, if you have f of nt, from that you get your nt plus 1, right? Now, in order to go from t to t plus 1, you need the realized growth rate, correct? In that part, the C is not playing a role, because whatever the realized growth rate might be, 10 individuals are getting added or 20 individuals are getting added. Samjhe?
Yes, but the realized growth rate, that depends on the total number of individuals at a given time, right? It's
so that is why I am saying that is it is in that sense that the C is independent of the realized growth rate.
Yeah, but the realized growth rate is not independent of C, right? C affects the realized growth rate, right?
No, it is not. If you look at the formulation, it is not. Just look at the formulation. No, f of nt plus C. So you calculate the f of nt and then you add C to that. So when you are going from t to t plus 1, nothing is happening. But now your total population size has become f of nt plus C. So in the next generation, it will enter into that realized growth rate.
Okay, so for the current generation, it won't affect the growth, but for the next one, it will.
Yes, absolutely.
So it kind of introduces a lag, right?
It is kind of introducing a lag, yes.
Okay.
Okay, chalo. So 45 minutes are over. I think what I'll do is I'll stop the recording. Hopefully this people have anyway started leaving, so I guess it's not a problem. Okay, Anand Krishnan, are you around? Anand?
Yes, sir, I am here.
So this is going into your Google Drive. So please make me the owner, huh?
Oh, sure, sir. Sure, sir.
Okay.